I misunderstood. So when you say, okay, maybe, fine. So yes, when you say this year, you meant this winter, the coming.
Oh yeah.
I see.
Right.
Got it. Well, it's great that I noticed you've been giving talks. So yeah, it's good that. So is there anything that I should mention during introduction?
Yeah, I think that's fine.
Okay, all right, no worries. Yeah. No pressure. Yeah, so most of the people will be here, but we might have, yeah, we already have a remote attendance here.
I see. Yeah, good to see you.
Oh, yeah. I haven't seen you for a while.
Do you have any plan for the summer, like the attending some conference?
Yeah, I'm going to ask it. You?
Yeah, I'm going to like the TASI summer school. Oh, for the aspect of global symmetry. That's
Oh, I see. That's nice.
Yeah. And then maybe apply for Princeton summer school.
Oh, okay, that's a short one.
Yeah.
Should be fun. Yeah.
Like 1 week. Princeton one.
Yeah. Apparently, many people are going. Maybe is there more than just a summer school? Because I know that there's a summer school, but I also know a couple of people are going, and they're not listed as the speaker. But so I imagine there's some other thing happening at the same time.
I don't know.
Yeah. Well, anyways.
Yeah. They seem not have a detailed information about that summer school. They're still planning.
I see. Still, wait, but it's okay. Coming in what, like 2 months or something?
Yeah.
Okay.
Yeah.
Okay. They must know what they're doing. So.
Hopefully. Yeah. So you this time is still in your like spring semester?
That's correct. Yeah, we have a semester system, right? So different from UC. We are 1 week away from wrapping all the lectures.
I see.
The finals will be in about like more than 2 weeks.
I see.
This is what the middle of the spring semester quarter for you guys.
Sorry?
It's the middle of the spring quarter.
Oh yeah. That's correct.
You have to teach, or you don't have to.
Yeah, I'm TA, like for the
TA.
quantum mechanics.
Oh, okay. I see. I'm teaching quantum mechanics this semester.
Oh, okay.
How are you doing generally?
Like the research?
Yeah, just everything. I guess I noticed you've been giving talks on this topic.
Yeah, right. So yeah, right. We're still working on like some experimental signature of the SMG and more physical understanding of this transition, and maybe some exotic Fermi liquid phase.
I see.
Yeah.
So when you say experimental evidence, you're talking about
like the spectral function.
Interesting. I see. What would be the candidate material for this?
Yeah, we are thinking actually maybe the pseudo gap physics can be applied this mechanism can apply to the non-Fermi, maybe understand the still gap physics, but it's still ongoing. Maybe let me try to share the screen.
Oh, yeah, that's great. Yeah. And people start to trickle in. Usually at 3:30, so
Can
let's wait a
you
couple more minutes. Yeah. Looks good.
can you see my cursor? This
Yes.
point.
Yes.
And this talk will be like 40 minutes and plus 20 minutes questions. Is that correct?
We usually have a lot of questions during the talk, so
Okay.
overall it's an hour thing, but if you need a few more minutes, that's totally fine.
Yeah, sure.
Uh, Okay, Da-Chau, I think, how about we start now?
Yeah, sure.
Okay, so yeah, so today we are very happy to have Da-Chau Liu visiting us virtually from UCSD. Da-Chau is a student of Professor Yizhuang You at UCSD, and they've been developing this technique called symmetric mass generation, which uses non-prohibitive effect to remove gapless degrees of freedom, including Da-Chau's or Fermi's. So Da-Chau, please take it away.
Yeah, thank you, Charlie, for the introduction. And I'm very glad to have this opportunity to give the talk on our recent work about the Fermi surface anomaly and symmetric mass generation. Yeah, so this work is done with my advisor Yizhuang You and Meng Zeng from UC San Diego and Zhuwen Wang from Harvard. So this talk will mainly focus on these two archive papers about the Fermi surface anomaly and the Fermi surface symmetric mass generation. So I would like to motivate this talk by reviewing the Fermi liquid and some effective action description of the Fermi liquid. And feel free to ask any questions if there's something that confuses you or something I need to clarify. Yeah, the low energy excitations of the Fermi sea are the gapless particle hole pairs around the Fermi surface. So there are electrons at P1 and hole at P2. Then this action is given by this free fermion operator, free fermion theory. And the Fermi liquid is quite stable because for generic Fermi surface, the four fermion interactions are marginal or irrelevant. Then this their interaction strength will decrease under the RG flow and recover this Fermi liquid fixed point. And more recently, there's a new archive paper studied the non-forward scattering, also includes the non-forward scattering and use the functional renormalization group. They find that the Fermi liquid is stable against even a finite interaction. If we focus on the low energy theory, we can linearize this Fermi liquid theory. Then that becomes a circle of gapless fermion, depends on this moment yeah, like a circle of gapless fermion if we are in 2+1D. So despite this Fermi liquid is well known in solid state physics, we want to ask the question, what protects the gaplessness of the Fermi liquid? Because there are many recent understanding about the gapless quantum physics of matter arise from anomaly and emergent symmetry. I would like to, yeah, are there questions?
I think this one.
Yeah, let me maybe talk about like 2 examples and then come back to the Fermi liquid. The first one is the deconfined quantum critical point. It describes a quantum phase transition between 2 symmetry breaking phases, the new phase and the valence bond solid phase. So for the low energy theory, this field theory has a mixed Tohov anomaly of spin rotation symmetry and lattice rotation symmetry. This mixed Tohov anomaly of such symmetry guarantees the low energy phase should be gapless, spontaneous symmetry breaking of either symmetry or maybe topological order. And this critical point has this mixed anomaly, of course. And this critical point also has an emergent SO5 symmetry that rotates new and wavy S order parameters. There are another maybe more recent understanding of the Ising criticality. If we take just the Ising chain and tune to this Ising transition, if we include both the Z2 Ising symmetry and the dual Z2 symmetry, we will get this combined like the categorical symmetry, and the critical point is protected by this categorical symmetry. This categorical symmetry has a non-invertible anomaly, and we may consider it's coming from the bulk topological order. So these 2 examples shows that the critical point actually has the emergent symmetry and some anomaly associated with the symmetry. Let's come back to the Fermi liquid case. If we write the Hamiltonian for the Fermi liquid, they're depending on this density operator and this theta parameterizes this Fermi surface. If we just for simplicity, we can think about the circular Fermi surface. And this Fermi liquid has an emergent loop U1 symmetry. What does this mean? It means that we can rotate the Fermi operator at a different theta angle by a different phase. However, this phi theta phase should be a continuous function and has the equivalent relation with the periodicity 2 pi. This may be very abstract, and let me give you some example of the subgroups of this loop U1 symmetry. So we can like decompose this continuous function to like Fourier series, and for the constant part, this corresponds to a total U1 symmetry. So it rotates the fermion operator on this Fermi surface by a constant phase rotation. And then this is a p-wave-like subgroup, and it corresponds to the translation symmetry because it rotates the phase, opposite phase at the right or the left part of the Fermi surface. This corresponds to a translation symmetry in the horizontal direction, and this translation in the vertical direction. There are also higher order terms like the D wave-like phase rotation and maybe F wave, I wave, G wave like the phase rotation, but they are more abstract and we currently do not have a good physical understanding of this higher symmetry, higher order subgroups. It's always good to keep in mind of this total U1 symmetry and the translation symmetry. Because they certainly have the physical meaning in the UV lattice model. So in the UV lattice model, we have the U1 symmetry and translation symmetry. this two symmetry has a mixed Tohoff anomaly. This is something like the generalized Lipschitz Matisse theorem. And so this anomaly is a renormalization group invariant, means that if we add some symmetric operator and run the RG, this anomaly will not change. But it should be appear in this emergent loop U1 symmetry. So symmetry with the Tohoff anomaly cannot be implemented in an on-site way. But if we in the field theory, most global symmetry are implemented in an on-site way. So this corresponds to some anomalous theory, and we need to cancel this Tohoff anomaly by attach the anomalous theory to a block with the SPT order. And then here comes the question: how do we understand this Fermi surface anomaly, and what's the bulk of this Fermi surface? So here comes to the outline of this first part about the Fermi surface anomaly. I would like to propose that the Fermi surface can be thought of the boundary as the phase space chain insulator. There are two ways to see this. One is that if we do the dimension reduction, we can get the Fermi surface as the H mode of the phase space chain insulator. Another way is we calculate the response theory, and this capture the many information of the Fermi surface. At the end, I would like to classify this phase space chain insulator, and this is correspond to the synthetic dimension reduction procedure. It's also Charming has this work on this dimension reduction, and using this method, we can get the phase space chain insulator actually correspond to the classification of 0 plus 1D SPT. At this point, are there questions or general questions? Okay. Yeah, if there are a question in the chat, maybe I cannot see from my portal, so maybe you can remind me if there are questions in chat.
All right, I will do that.
Yeah. And let's do the first part. How do we write the phase space chain insulator? So let's just first focus on a very simple 1 plus 1D example. The gapless fermion contains the left moving part and right moving part at the Fermi points. It's very tempting to just place this chiral mode on a chain insulator but in phase space. So the x direction it's a real direction, and the vertical it's a momentum axis. And this chain insulator is infinitely long in the x direction, but has a boundary at these two Fermi points. Let me remind you of the chain insulator in real space. So we have this polymatrices that they are anti-commuting with each other, and the mass profile is negative inside the material and positive outside the material. So there will be a chiral H mode along the boundary of this material. But for the chain insulator in phase space, let's first forget the x and k do not commute, and write down this phase space chain insulator simply by replace the vertical direction by a momentum coordinate. But we know that this x and k do not commute. So there are two ways to recover this commutator. One is using the canonical quantization to replace the operator by a partial derivative of vice versa. Another way is to thread a uniform magnetic field through this SK plane, such that we can project this theory to a lowest lambda level, and then x and k do not commute. So in the following, for different purposes, we will use one of this method, but not both, since using one is already good enough to recover the commutator relation. And let's do the dimension reduction to recover the Fermi surface from the phase space chain insulator. So still this 1D example that we design this mass profile to be negative inside the two Fermi points and positive outside the Fermi points. Then, because of this mass profile has this sign changing at minus KF and KF, there will be localized mode at this at these two edges. And if we project this theory to this low energy sector, then we will get two localized chiral modes that reproduce the left moving and right moving modes in the Fermi liquid theory. So this one plus this, how to say, this two in phase space, we always like have 2D plus 1 dimension, and this 2 plus 1D phase space chain insulator will recover the 1 plus 1D Fermi liquid theory. And it's easy to generalize to higher dimension. In higher dimension, we have the phase space chain insulator in 2D plus 1 dimension. And for the Hamiltonian, we can write in this form. This gamma x and gamma k and gamma 0 are anti-commuting, and they are from this complex Clifford algebra with 2D plus 1 elements. And we also design, yeah.
Oh, sorry, may I ask you if you're gonna answer that later, it's fine. Can wait. So earlier you said that there are two approaches. Either is to treat K as partial X to account for the commutator. The other method is to put in a magnetic field. In the treatment of the Chern insulator, which one did I use? Or did we use?
We will use this canonical quantization, and I will show this later.
But the edge-most stuff has nothing to do with this yet.
This because it's in 1 plus 1T, but in higher dimension, you need to use the anti-commutation relation, use the operator relation.
Right, but why in 1 plus 1, I don't care, because if I look at the first line and I have to make a choice, right? So it's probably not wrong to do that.
Yeah, because maybe for example, I think this case already breaks the translation symmetry in K space.
Okay.
And if we want to use that operator relation, we somehow need to like have this I partial K does not have this mass term depend on the specific. Like this mass term okay, maybe let's go to the higher dimension case, and that will show explicitly how this operator relation will be used. Yeah, this actually is the next slide. So so this is our the phase space chain insulator in 2D plus 1 dimension. And we have this mass profile negative inside the Fermi surface and outside the positive outside the Fermi surface. So let's maybe project this to in one direction. Let's say this K1 direction. If this mass term, so this mass term, we just maybe first focus on this changing sign along this K1 direction, and then there will be. Because of the sign changing, then this MK1 will pair up with I partial K1. There will be a localized mode at when K1 goes when the mass changes sign in this K1 direction. So this part will be project out to the low energy sector, and but we still live with many partial X and partial K in this Hamiltonian. Next, we can use the operator relation to replace I partial K to X. So we replace this I partial K2 to I partial KD by X2 to XD. This uses recover the commutator between X and K and now we only have this this part has been project out, and we replace its I partial k to x operator. And we can see that this x also correspond to many domain walls in the x2 to xd direction, because in the left part the x is negative, and in the right part the x are positive. Then they are creating many domain walls when this x changes sign to x equals 0. Yes. So then this will pair up with all the I partial x2 to I partial xd, and if we project to the low energy sector, then they are gone. We only live with this I partial x1 and this part. So I partial x1 will be the if we along this k1 direction, and that's correspond to the chiral mode in this x1 direction. We can do this projection for like the arbitrary angle, like the k1 is the cosine theta and k2 is sin theta, and we can project along this direction maybe. Then that will give you another chiral mode along the normal direction of this Fermi surface. So afterwards, we will get a bunch of this chiral fermion along the normal direction of the Fermi surface. Does this make sense?
Just one small question.
Yeah.
Is it clear to see that this Hamiltonian or H bulk is bounded from below? Like it seems like you can make X arbitrarily large and negative, right? Or so
sorry.
I mean, is it like a well-defined H in the first place? Because you can make X arbitrarily large and small, meaning that like large in absolute value and small and negative.
X corresponds to the coin.
Sorry. Yeah.
So sorry, you're asking about this the X here?
Yeah, I mean, it seems that okay. I'm not sure.
Yeah, this X is a coordinate for the real space. Like this X will always change its sign at X equals to 0. That's a crucial thing that will localize your mode at X equals 0. This domain wall.
Just to help out here, so Felipe's question is whether or not this Hamiltonian is bounded from below, and if not, what happens? And the answer is it is not bounded from below. And it is what it is in the sense that if you try to expand around the Fermi surface, you don't know where the band bottom is. And we just live with that. It is bounded from below, but not at this level. It's supposed to be something.
Yeah.
Thank you.
Sorry, my audio is quite bad. I cannot hear this. Yeah, right. Yeah, this X. Right. I think you have clarified this point. This actually, we can actually put this phase space chain insulator in a lattice. Then maybe you can see how this operator do the Fourier transformation and what's the bound for this X and K.
Yeah, so that's what I ask. It's pretty much the same question. So there is a first step, which is to project out certain things, right? And then why, when I do that, I don't need to worry about the commutation relation between X1 and K1.
Because yeah, I'm thinking maybe one way to understand this is that you can make this X and this mass profile change sign some momentum point, and that momentum point does not overlap with the real space coordinate. So Yeah, it's like the x coordinate actually, if you do the Fourier transformation, they are parametrizing some finer structure of your momentum space. Yeah, let's take this x1 and k1 on a lattice. And the k1, you can imagine that k1 and x1 both have a very large lattice spacing. Then this k1, this k1 corresponds to a large momentum modes.
Okay.
Right. This is an assumption, and then we do the Fourier transformation of the x1. So because originally the lattice spacing is large, you do the Fourier transformation, then the corresponding momentum is actually have a small spacing because it's 2 pi over like 2 pi over a. The distance, if the a is large, then this dual momentum variable will be very short spacing. That correspond to some small momentum transform modes.
Okay.
Yeah.
Yeah, I couldn't quite follow, but I guess naively, maybe this is something I should understand offline, but just naively, it seems like you treat the one direction differently compared to other directions.
Yeah,
And
that's correct.
All that difference is because that you turn on a mass term. And
yes. Uh-huh.
Yeah.
Yeah, and this mass term defined in this phase space and depend only on this phase space momentum coordinate. Yeah, we can discuss this later because there are more like interpretation of this thing. But at this step, we kind of treat this mass term. We first project this project out the localized modes localized by this mass term, and then use operator relation to project other kinetic term to get the Fermion along one direction. Yeah, we can come back to this issue later and discuss more. Okay, yeah, so we reproduce this Fermi surface from the bulk phase space chains later, and there are directional Fermions matches with the low energy degree of freedom of the Fermi liquid. And this also has this emergent loop group symmetry that you can rotate the Fermi operator by a different phase along this Fermi surface. And next part, let's talk about the response theory, such that we can see some information from the Fermi surface. So like the ordinary chain insulator, this theory can be minimal coupled to the background gauge fields. And after integrate all the fermion, we will get the Chern-Simons term. Because of this this k-dependence mass term, this Chern-Simons term will only live in this between these two Fermi points. And then we need to impose a commutative relation between the x and k by using this uniform magnetic flux. So we can reproduce the Latinger theorem. For example, we can do the variation with respect to A0. This corresponds to the fermion density. This will show that this failing is given by this response of this response theory. This can be generalized to higher dimension because in the phase space, we always have the 2D plus 1, which is an odd number, and we will have the bulk Chern-Simons term in this odd number dimension. But we need to remember that we need to thread the magnetic flux through every xi ki plane. Here maybe comes to a comparison that maybe we can compare the Fermi surface in 2 plus 1D and the well fermion in 3 plus 1D. So both of them have this ADABA Chern-Simons term. But for the Fermi surface, we argue there will be this xi ki flux through every, there will be flux through every xi ki plane. And certainly this response theory are different between these two theories. and their anomaly are actually quite different. For example, we can break the U1 symmetry to Z4. Then for the Fermi surface, you can imagine you can write the Hamiltonian, that's the fermion hopping on the lattice. And at each lattice side, we can add this charge 4e interaction through all 4 copies. Then if we go to a large interaction limit, this will give you a product state, which is a symmetric and unique ground state. Means that if we have 4 copies of this system, we can trivialize the system by adding this interaction. But for the well-fermion case, in 3+1D, if we break the symmetry to Z4, then it's a Z16 anomaly, means that only 16 copies of the Z4 symmetric well-fermion can be trivialized to have a unique ground state. Last, I'm going to talk about the classification of this phase space chain insulator.
So may I ask about the anomaly, the previous slide?
Yeah.
So maybe you're gonna explain, but what's making the there's this observation that they're different, but can I? What's done differently if I just want to say analyze the response theory, but at this level just break the symmetry to Z4? Can I think of it this way? Just look at the response, think about just some Z4 whatever gauge field stuff, and then can I see why one is Z4, the other is Z16?
Yeah, I'm not sure because this Z4 then corresponds to some non-perturbative anomaly, and for the AD8, this term only captures a perturbative anomaly labeled by the integer coefficient. Yeah, so maybe the point of this slide is just say that the response theory are different, and so is their anomalous structure.
Okay.
Yeah. Yeah, and for the classification, we start with this bulk phase space chain insulator, and here the mass does not depend on the momentum. It's a constant mass, a uniform mass in this phase space. We can again use the operator relation to replace I partial k to x. And as explained previously, that this x creating many domain walls along the x1 to xd direction at x equals to 0. So if we project to the low energy sector, then we get back this 0+1D system, just this mass term m Steinberger psi. So this means that this 2D plus 1 phase space chain insulator is actually a 0+1D topological insulator. And this M twins the topological transition in the bulk. So if the bulk state is trivial, if the gapless fermion modes at M equals 0 can be symmetrically gap out by interaction. Yeah, this is a Z4 example that we can add this charge 4 interaction to get a Z4 classification. So the general statement is that the momentum counts as a negative dimension. So if you want to classify the phase space chain insulator or other system, then there is an effective dimension, which is a real space dimension minus the momentum dimension. So let's take the example of in 3+1D, if we have the ordinary Fermi surface, then this corresponds to a 0+1D classification problem. With the U1 symmetry, you will get the classification Z, means that you cannot stack the, so if you stack many layers, you cannot add symmetric interaction to get a unique ground state. But for the Fermi rings, it corresponds to the classification of 1+1D system. This is 0 because the Fermi rings are not stable in this setting. And for the well points, the classification are 2Zs, they are corresponding to the like they are a surface between two well points, and you can attach Hall conductance or thermal Hall conductance to this interface. So this corresponds to these two Z's. And we can use this method to calculate many classification of very exotic group, not exotic, but maybe larger group or not abelian or non-abelian group, and even with this discrete group. Then the classification will give you the integer index correspond to many, either the integer or like discrete classification. I should say there is another part of this table. The Fermi surface anomaly actually also has a part from this fading, and I will discuss later in the symmetric mass generation part. Yeah, the last part talk about the general anomaly of the Fermi surface, and we can use use the condition to investigate this Fermi surface symmetric mass generation. So maybe first, what is this symmetric mass generation? It means that we can preserve certain symmetry and give the gapless fermion some mass. So there are two ways to say the mass. One is you diagonalize your free fermion Hamiltonian, then you can say there's a gap in the dispersion. Another way is to to calculate the two-point correlator. You can say exponential decay indicates this many-body excitation gap. So this method is valid in the interaction with interaction. And generation means that it's a dynamical process. We want to turn on some symmetric interaction that develops the multi-fermion condensation that preserves the symmetry and open the gap. So there's a necessary condition for the SMG. It's anomaly free. So why do we care about that? So usually the Anderson-Higgs mechanism, we want to condense the fermion bilinear to give a mass, but this will necessarily break the symmetry, so it's not a symmetric. And this method can be used to realize chiral fermion in the lattice model by symmetrically gap out the mirror sector. This was proposed in H. Imprescu 1986 paper, and recently numerically conformed in a 1+1D model. So for the Fermi surface SMG, it may be used to understand the large Fermi surface to small Fermi surface transition, a pseudo gap in the cuprate superconductors, and some charge 4e pairing. To be concrete, yeah, and this is so for the SMG we need like the anomaly free condition. The Fermi surface anomaly should vanish. Then we need to calculate this anomaly index to show whether the system can be symmetrically gapped or not. So this anomaly index contains two parts. One is this integer index, as previously classified, and another part is this failing. So we take the U1 example, then this integer coefficient correspond to the charge times the multiplicity and their plus or minus sign for the electron or hole-like Fermi surface, then times with this foaming volume. So a very toy example is we have two types of fermion, A fermion hopping on the Kagami lattice, and B fermion hopping on the triangle lattice. A fermion is charge 1 and B fermion charge 3. If they are failing to satisfy this condition, then this anomaly will vanish. And since the symmetry is restricted enough, it can forbid any fermion bilinear condensations. If we have a charge sensitive wave, this will break the translation symmetry. If we have the superconductivity, then this will break the U1 symmetry. However, it's possible to add a symmetric interaction, something like this form. it's annihilate 3 fermion on the triangle to create 1 fermion on the of the type B in the annihilate 3 fermion on the Kagami lattice to create and create 1 fermion on the triangle lattice. So if we drive this interaction to a strong coupling limit, you will get a unique ground state, and it's also a product state. So there must be a phase transition between the Fermi liquid phase and this SMG phase. This unique ground state is certainly different from the Fermi liquid state. Then we did the renormalization group analysis of this model. So we tuned this tuned to a very specific fitting such that the Fermi surface contains these Van Hove singularities. And we can, most of the density states are at this Van Hove singularities, so we can approximate this Fermi surface by just 3 points. And there are 2 types of interaction in this momentum picture. One figure A is like dense density interaction, and figure B is charge fusion interaction, corresponds to that symmetric charge fusion interaction. And both all these for 4 fermion interactions are marginal, and depending on this depending on the initial value, it could be relevant or irrelevant, marginally relevant or marginally irrelevant. So the phase diagram would look like this. So there will be a Fermi liquid phase and SMG phase. So there will be a phase transition between the 2 phases, but the precise critical field theory we currently don't know. It's also an very interesting to study what the critical theory describes the transition. Yeah, with all of this, let me conclude. So in the first part, I discussed about the classification of the Fermi surface anomaly. In general, the codimension P Fermi surface anomaly of symmetry group G is classified by the G interacting SPT in P dimension space-time. It's and maybe, for example, the general Fermi surface or the ordinary Fermi surface classified by a 0+1D SPT. And the Fermi surface symmetric mass generation can happen when the Fermi surface anomaly vanishes. This can potentially used to understand the pseudo-gap physics, and there are also spectral signatures. For example, the Green's function 0 will appear on the Fermi surface in the Fermi liquid phase. I mean, in the SMG phase, the Fermi liquid, the Fermi surface are replaced by the Green's function zeros. And there are many very interesting future directions. Yeah, with this, I thank you for your attention and questions.
Any questions? Myself?
You mentioned something about symmetric mass generation, helping to explain Fourier pairing or giving a mechanism for Fourier pairing, right? But can you elaborate more on that? Did you hear me? Sorry. So you mentioned at some point that with symmetric mass generation, you could provide a mechanism for Fourier pairing.
For Fourier pairing, yes.
Could you elaborate more on that?
Oh yes. So basically, if we like maybe let's go back to this example. Oh, sorry. Let's go back to this example. So if we have the U1 break to Z4, then we add this psi1, psi2, psi3, psi4. This is the charge 4e interaction. It's Z4 symmetric, right?
I see.
Yeah. Basically use this interaction to get the symmetric gap phase. If you tune this interaction to infinity, you will get this 0, 0, 0 plus 1, 1, 1, 1 state at each site.
Okay.
Mhm.
Thank you.
Yeah. Here, the main point of this symmetric mass generation is that we don't want to condense the fermion bilinears because the fermion bilinears are charged under the global symmetry. But if you condense the multi-fermion operator, then it's a singlet under your global symmetry.
Okay.
Other questions? I have a question really just about notation. So you have a table with a lot of loop group stuff on it.
Yes.
When you say loop group, do you really mean loop group, or you mean that group on some whatever Fermi surface? Because loop group specifically means a loop of that group. Means if you really ask, it's about Fermi surfaces in 2 dimensions. Yeah.
Oh yes, that's correct. This loop group yeah, you are right. So the loop group are specific for this 2 plus 1D Fermi surface. But since our classification shows that the general ordinary Fermi surface correspond to 0 plus 1D SPT, then this you can change this L to maybe other like a sphere to group. So by definition, this loop group is S1 to G, and for general dimension, it's SD to G, for example. If you have a 3D, yeah. Yeah, and maybe for some of the discrete group, it's much more subtle. And what we are really thinking about is use the wave decomposition picture. You have the S wave, P wave, D wave, and so on. So you break you see whether the interaction will break each element to what part. Mm-hmm. Like, yeah, for example, the charge 4E interaction will break the S wave part to Z4, but will not break the P wave part, because you always have the antipodal for interaction. This will not break the P wave part. Mm.
Okay. Any final questions? Okay, I guess if not, let's thank our try again.
Yes, thank you.
Meredith, you can probably